start thinking again about our time together. When the night is over, my life is over. 'Cause I start thinking again about our time together.
Say the word, say the word. Say the word, come on. Say the word and we can run around the earth and around the sun. Say the word and we can stay. Forget about that better place. And I know you're healing, 'cause I know the feeling. The streets stop breathing. Don't wanna say, say, say. Say the word, say the word. Say the word.
Seeing all the reasons we should forget about this place, but I don't wanna leave here if you're just gonna stay. Changing like the seasons, been wasting all this time. Should be like satellites, cast beyond the sky. Leave our fate for another day. Riding these horizons, we'll find our way. We'll leave our fate and fade into the night. Just follow me to paradise. To say we tried.
Say the word and we can run around the earth and around the sun. Say the word and we can stay. Forget about that better place. And I know you're healing, 'cause I know the feeling. The streets stop breathing. I don't wanna say, say, say. Say the word, say the word. Say the word. Say the word and we can run round the earth and around the sun. Say the word and we can stay. Say the word.
You see the sunrise in front of us. Eyes are like our thoughts and stories told me shadows that really create innocence. Counting down, we're counting down to the endless.
Good evening to everybody, and welcome to our October DevClub event hosted by our sponsor Transferwise. Excited to be here. Excited to see you all here. For today's agenda, we have three talks. First is by the host, Dmitry Zhukov from Transferwise will talk about the Apache Spark and how to use it in production, experimenting, as you can guess it from the title. And then second talk is by game engineer Filipp Keks, who is also an often guest at DevClubs, who is now at Wolf 3D, and he will be talking, of course, of mobile graphics. And then the last talk is also by one of our sponsors, Nortal. Erkki Alamäe will give an introduction into the data. Before we crack on, there was an office tour before the event. Ivo, can I have next slide, please? And by the data we gathered from ticket forms, almost 80% signed up for office tour. Can you please raise your hands who actually went to office tour? Okay. Please keep your hands up who enjoyed it. All right. I also went to the tour and I also enjoyed it. I think Transferwise guys have really awesome office. And another thing we ask you in the ticket form is like, what programming language do you normally use or you prefer to use? Java appeared to be the most popular one. Java appeared to be the most popular one. And then Python and JavaScript came along next. And well, some people apparently decided to be the smartest ones and submitted English. So just so you know, you were not alone. There was 4 of you. That's it, I think, from my side. We'll pass the mic to Dmitry, and please welcome him on stage.
I have a microphone here, so thank you very much for coming here. We are always glad to host DevClub and the old engineering community of of Tallinn and Estonia. I want to speak today about the topic. This is the continuation of the topic I was speaking about 1.5 years ago at the same stage. It was hard to start speaking back then, and it was hard to start a machine learning project back then. Today, it is still hard to start speaking, but I hope it's a bit easier to start a machine learning project. For many companies, fraud detection becomes the main driver behind embracing machine learning techniques. Transferwise is not an exception. Our fraud prevention team started experimenting with machine learning in the late 2015, and we've put quite a lot of effort into it. And with this effort came experience that we actually want to share right now with engineering and data science community. Before diving into details, I wanted to introduce you what actually fraud detection is, because it's our example. Transferwise is a money transferring business. An individual given a credit or debit card can transfer money from one country to another just by knowing a credit card number. And if this credit card number was acquired illegally, then this individual is called fraudster. Fraudsters are statistical anomalies, and this is how we try to find them. Let me give you an example. Imagine not a young customer from US making transfer to somewhere to Russia with an Estonian IP. If you look at the picture, it doesn't pass reality check. Statistically, these kind of customers don't exist in real life, and there are just no good customers that have the same combination of parameters, and we try to find such parameters, and this is where machine learning kicks in. Machine learning is not a young field anymore. It has its roots in optimization, combinatorics, and these fields appeared long before transistor appeared. But it had limited application before internet scale volumes of data. And today, spam and fraud detection is already a classics of machine learning, where it truly shines. So for us, it was not a question whether we should start using machine learning or not. We just needed enough data to learn from. Here you can see the yellow bar. This is where we trained our first model. We had to collect quite a lot of data, labeled data, before we actually can train something. And while we were collecting it, we could easily and silently fix our technical debt problems, which I was talking about on my last speech at DEVCLUB. The first model that we built was built on top of our rule engine. In our rule engine, each triggered rule gives a score, and usually it's a hard-coded score. Then we sum the scores up and compare it to the threshold. If value is above threshold, we raise suspicion. It's a very simple thing, but it's sure the scores assigned to the rules and the threshold itself are not optimal. We tried somehow to think how we can optimize that, and came up with an idea that we just treat our rules as features of a machine learning algorithm. And we trained a machine learning, a random forest on top of it. And since then we never regretted that. And at this picture you can see a classical ROC curve for our rule engine. This is the blue line, and the new random forest model. So this was trained on Spark 1.6. It would immediately give us quite a good benefit. We either could decrease false positives by 30% or increase true positives by 10% with almost no effort. At least we were thinking so back then. Okay, so we've got our model. I trained it on my machine, but there is a chasm between your sandbox, where you play with machine learning, and the production deployment. There were gaps to fill in, and one of the major problems was the question whether we're actually using the right framework. I've chosen Spark just as a tribute to hype and fanboyism. I like it, but is it really something we should stick to? So we came up with a list of requirements to choose Spark ML machine learning framework. Sorry. So it should support saving and loading models. Models should support changing of arbitrary transformations using pipelines. Models have to be able to be loaded into JVM process so that we could run it in production in our Java environment. The framework should be scalable to scale up to hundreds of thousands or hundreds of millions or billions of examples. Python API would be a plus for sure. Prior experience with the framework is also a plus. And the last, but probably the most important thing, was that we wanted a single execution path during training and production when we are running models in production. Most of these are quite self-explanatory, but I wanted to draw your attention a bit more to the last point. So what do I mean by single execution path? There are three chronological steps in the life of every machine learning model. First, you do training, where you get the model itself. Then you run testing, where you run prediction on your test set and measure performance. And the last thing is the model gets to production, where it actually makes prediction and you make a decision on top of that prediction. At every step, data undergoes some transformations. And the hard part is to ensure that these transformations are doing exactly the same thing in on offline training flow and online production flow. It very often it is done so that one code base is used for training, for example, scikit-learn and Python code, and completely another for running in production, let's say JPMML, which stands for Predictive Model Markup Language, whatever. And there is no maintainable way to guarantee that implementations of models in scikit-learn and this JPMML are actually doing the same thing. So, machine learning engineer ends up with the following options. To use one framework for all of this, or to use two frameworks, one for training and testing and another for production flow, or maybe to have one framework for training and another for testing and running in production. The first case, when there is a single framework, is the most desirable. For sure, it simplifies things. You don't need to care about compatibility between those frameworks, and updates to software becomes much easier, and you don't need to have parity tests between your frameworks. Second option, when you have your training happening in one framework and testing and online prediction happening in another, is kind of okay, but it puts additional effort on analyst. So he has to juggle two frameworks when training a model, while training and then testing, passing data between those is also quite difficult, and this burden lies on shoulders of data analysts, and depending on their coding skills, maybe it may become unbearable. And the third option, when you have training and testing happening in one framework and the prediction happening in another, this is simple for data scientist. He stays within the same framework, but it requires some effort from engineers, because now you have to, when you deploy a model to production, you actually don't know what you deploy, because there is completely different execution path happening in production, and this is, you need some facilities to test models in production. This is the reference to the title of my presentation. Luckily, this kind of framework to test models in production is very helpful by its own. You are not guaranteed from mistakes even if you are using one framework. So it also follows the best practices of gradual rollouts and A/B tests. So you first deploy model to production in the shadow mode. It runs for a while. You collect statistics, see that it works as you want it to, and only then you switch your production flows. The downside here is that is the feedback loop. You have to wait for a few weeks maybe to collect this statistics. Otherwise, you can't make a decision. At the point of time when we were choosing our framework, the only framework we found that supports all of these requirements was Apache Spark 2.0. And the problem was that it was not released yet. So we were thinking what to do, but okay, we thought, okay, running snapshot probably is fine. Okay, but don't try it at work. The only thing that we needed to do is actually to smartly mitigate risks. So we needed a proper monitoring of models that are running to see how they perform, what is their latency, speed, and actually the accuracy they give. Additionally, if machine learning process fails, there should be a safe fallback. In our case, it was our good old scoring rule engine. But even if everything fails, the machine learning models should not be put into a critical path, so that customers are still served even if everything fails. Surprisingly, it worked well. We didn't experience any issue related to the nature of snapshot nature of Spark 2.0. That was we were just lucky. But this is something I can't tell about the Spark in general. So we decided to go with Spark, but how we should run it. There are two modes that Spark can operate in. There is a cluster mode and a local mode. In cluster mode, every principal component of Spark runs in its own process. This requires quite a lot of orchestration and operational work, which we didn't want to have. In contrast, there is a special local mode that runs all the pieces of Spark in the single JVM process. And it is looking very appealing. You can actually put the whole Spark into a Spring Boot application and serve your models through HTTP API. There was one problem though, that this mode is actually designed for running tests, but since we're breaking bad with snapshot, who was caring? We decided to run it in local mode. It simplified everything. Releases could have been done using our existing facilities. No need to operate cluster. Package updates are simpler. Security surface is pretty much the same.
Do you mean only one instance?
So we are running multiple instances of microservices anyway. So and there was a single Spark instance within instance of our microservice.
But still one instance of Spark application.
Yeah, within JVM process. Yeah. So we decided to go with Spark running in local mode within a Spring Boot microservice. And this is when we started, and we got problems for sure, like anything. And it was known from the start that there will be some problems with latency. We made some tests. Every time Spark starts a task, it goes through all of these principal components, even in this local mode, and it takes quite a lot of time. Also, Spark has quite heavy task serialization, deserialization procedure, and with very large tasks and machine learning tasks are quite heavy, like any one model can be up to several megabytes or even tens of megabytes. It could jump the latency could jump up to seconds. For our first model, it was not that big. It was between 2 or 4 seconds, which was considered acceptable at that moment compared to, for example, our data gathering latency. What was a surprise for us is when we trained our completely new model, and this new model was not relying on our rule engine rules anymore. So it was a completely different set of features with a lot of categorical features that required string indexing, and the random forest itself was of a completely different scale. There was hundreds of trees with quite high depth. Yeah. And when this pipeline that we designed was just too big and the latency just jumped to up to 30 seconds, and it was absolutely unacceptable. Additionally, when Spark submits this task, it creates a lot of small Java objects, and 1 or 2 gigabytes of them. And imagine this on every HTTP request. Basically, it was just trashing garbage collection, and we had, you can see at this graph, garbage collection pauses up to several minutes, and every day our services started crashing out of memory. So there was only one solution, just to switch it off. And so what? Game over? No. So there were 3 ways out of this solution. Just get rid of Spark, find another framework, another framework to rule them all. It was hard to choose Spark, and there's probably no or almost no other frameworks that support all the flows. Another option was, so we didn't consider this option, dumping Spark. So because the transition wouldn't be flawless anyway. Another option was to contribute to Spark to make it faster. By that time, I already knew some Spark internals, and I understood that it's just too heavy task for us to handle. There are several parties that tried to do that and still trying, including UC Berkeley and the Databricks, the developers of Spark itself. So we were left with only one option, is to have 2 frameworks running. So no single execution path anymore. And the obvious solution for Spark was to have mleap as a second framework to run in production. mleap is a lightweight execution engine for Spark models, and not only. It actually also supports scikit-learn now in TensorFlow. It doesn't support training. The only thing it does, it can serialize models, load them into production process, and execute them very fast. This framework matured a lot since we started our machine learning experiments, and it convinced us to try it. But what move to mleap mean to us? So, as I said, no single execution path anymore, but luckily at that point we already had this production model testing facilities. So we were running models in shadow mode as a routine by then. And yes, this is the looking back at our diagram. Spark was used to train and test models, and mleap to run predictions. Also, it was since mleap actually supports almost all of the Spark models and transformers, except one, SQL transformer, and which we were using in every model. So we had to rewrite all of our models, our feature generation, and retrain everything. Another thing is that it was clear that we will have to contribute to mleap, because there were some features in Spark 2.2 that we were waiting a lot, and mleap just didn't support them. So that was a good occasion to contribute to open source. From the bright side, we've got 50 millisecond latency compared to half a minute and pauses up to and crashes. And no GC problem whatsoever. Yeah, this is 95th percentile for peak load during the day. What other Spark issues I can tell you about? There are actually quite many small issues. I just have no time to talk here about them, so you can probably find me in corridors and ask. But one feature, problem that I wanted to say about is the random forest memory footprint. So we were hoping that Spark will let us scale to at least 100 million samples in the training set. But yes, Spark itself supports that, but the algorithm of random forest they have doesn't. With a 2-node Spark cluster with 60 gigabytes of memory each, we were able to train no more than 10 million samples. One thing that helped us, we switched JVM to G1 GC, garbage collection, and it helped. So we pushed we could train up to 15 million records now. So luckily, work on random forest doesn't stop, and there is a ticket in Jira, Spark Jira, that they are working on to fix random forest. With all that said, you can ask a valid question. What if I were to choose framework today? That's quite hard question. The world of machine learning literally exploded during those 2 years. Many frameworks that were not touching machine learning before now include machine learning as their official part. For example, Apache Flink, which is actually a streaming framework. Many machine learning frameworks now ensure you that they support production flows. And one of them, TensorFlow, got a major update in the beginning of this year, and they have now Java API to integrate into your Java processes. Also, they include TensorFlow serving, that you can serve models from Docker container. Also, Spark is is not standing still. They have now plans to have low latency streaming, continuous streaming engine. They try to push it to version 2.3. I doubt they will able to do that, but they will try hard. Personally, I would probably recommend today to try TensorFlow. This Java API feature is just making things so different, and features of TensorFlow and some architectural decisions they made just feel right. To finish with, I wanted to give you some hints to choose a machine learning framework. First of all, there is no a framework to rule them all. There is no framework that will solve all of your problems. Not all of your problems. Industry is just getting there. But keep searching. This is very important if you will be able to do all the paths in one framework. Never underestimate the complexity of production deployments of machine learning models. Data preparation, model handling, and all this stuff around constitutes probably 90-95% of all of the work you will have to do, and only left 10 to 5% is the actual fun of training. For example, we were not able to move significantly before we put 3 engineers on this topic. When choosing, look at the community. All machine learning frameworks and the whole field is evolving very fast, and if you choose a legacy, it can be a serious detraction. It's probably better to take some risk and mitigate that with monitoring and other tools. This may be game-changing for you. And if you have someone in your team passionate about some technology in machine learning, give him freedom. Probably this will be fun for him, and he will work hard. And don't spend too much time on choosing. Anyway, there will be problems, and you will have to solve them. Yeah. Thank you very much. Your questions?
So, on the website, do I need to use it? No? Hello? No. Okay, on the website, Spark says that it's lightning fast, and it's 100 times faster than Hadoop. And you're saying that it's mega slow, so what's the trick here?
So, yeah, there is a trick. Fast means throughput, not latency. So, with Hadoop, latency is even lower, but Spark has quite low latency if you have big models. If you have just a small real-time ETL that just transforms, like makes a count of some integers, it's a very small job that submits to Spark streaming, and it's fast.
Oh, sorry. Thank you. So can you talk a little bit more about the domain sale problem? You were talking a lot about the machine learning engineering part, but about what made, what data or what features made the machine learning model perform better than the rule-based agent? What were the possible probabilities that they pulled out, or
Okay, I understood the question. Thank you. So, when we were considering what to do with our rules to optimize them, I was staring at it for a few months, and finally I understood that it looks like logistic regression, just a hand-optimized logistic regression, and this is just a linear algorithm. So if you put non-linear algorithm, like random forest, it basically, no doubt it will find some corners that can be more optimal. Also, with our second model, the one that was struggling with latency, we completely changed our feature set. So it now included raw features that were input to our rule engine. And there it boosted our accuracy much more.
Well, there's actually more maybe. You are still a little bit stuck in statistics, in engineering, but actually maybe talk about the problem, about maybe the data itself. Or
The data itself.
if you know.
So I can say not that much about data because it's, you see, we are catching fraud here, and if fraudsters will know what we are actually using, they will be able to do their work more efficiently.
This one's also getting on the internet. So you know.
Yeah. Basically, if just to some examples, we use some features, and for example, source currency. When money is transferred, there is a source currency and target currency. These are obvious categorical features. Person name can be, email, age is actually the history of transfers, whether user already transferred has a transfer, for example, 2 months ago, which is already much less risky, and many things like that.
Can I ask one more question? Or does anybody want to go?
Why random forest, not neural network as we have?
Thank you for that question. First of all, random forests are very simple to use. So we were aiming to pick low-hanging fruits first, and random forest is just known to not overfit. We have quite a difficult domain in the sense that we have very imbalanced problem. So we have big class imbalance, like there are much less fraudsters than good customers, and random forests behave really well on that. There are articles in the internet covering the fraud detection topics, and every one of them gives performance for random forest as the best. Another option is actually gradient boosted trees. Is also tree ensemble, which also works best, good, and we are experimenting with that too.
Last question for this one. Anyone?
I can ask.
Yeah.
Did you
Go for
do
it.
any more feature engineering? What I mean is, did you look at the data more and said maybe we can drive something that we don't have yet before actually applying machine learning model?
Oh yeah, sure. The feature engineering here is like the most of the work actually. So you, I don't know, we have probably 100 or something features, and every one of them is hand engineered. This is not something you can do automatically at the moment of time. And I don't know if I give one example, another example of feature preparation. For example, there are categorical features that have too many categories. For example, you have a card number. There is a bin in front, 6 digits, and there are thousands of them, tens of thousands, maybe hundreds of thousands, and you can't just put this number into any machine learning algorithm because there are too many of them. If you want hot encode them, there will be so many. The feature vector will be too sparse to handle by any machine learning. Maybe neural nets, I'm not sure, after like 1 billion samples. We will see. But you have to do something with that. A random forest can't consume this kind of high cardinality features. So what we do, we actually transform them to ratio features. And this is this ratio. It's also called label averaging. So, for example, for one particular bin, we find how many good users they're using the same bin, and bad users, fraudsters, and calculate this ratio, bad users to good users, or all users, and provide it as a feature. This is it becomes now a continuous number, real number, and it's consumable by any algorithm. We sure lose some data there, but it's better than nothing.
Right. Thank you so much, Dmitry. Let's have a... Let's have a short break, around 10 to 15 minutes, and together here at the same place for a second talk by Filipp Keks.
Я prepared. Ты мне нужен для логинов вещей. Да.
I've seen you. I've patrolled these empty thoughts before, but I'm fixed now on the cure. I'm holding on to the last rock on the mountaintop, and I'm begging for your love. Do you remember the type of folk we used to be, and the simple souls we used to see? Do you remember a fallen man with no escape? It seems he lives in yesterday. If you play away, well, I forgive you once again. I'm losing patience, and I know for sure that we've been right here before. I see the dangers, baby, I'm not crying over you. There's no point denying we're through, 'cause baby, I'm not crying over you. There's just shit that I've gotta do, so I'm not crying. Just sleeps away and I'm eager for his break. Like a human chess piece I've been playing, you're coming back for more. Do you remember the type of folk we used to be and the simple souls we used to see? Do you remember a fallen man with no escape? It seems he lives in yesterday. If you played away, well I'll forgive you once again. I'm losing patience, and I know for sure that we've been right here before. I see the dangers, baby, I'm not crying over you. There's no point denying we're through, 'cause baby, I'm not crying over you. There's just shit that I've gotta do, so I'm not crying.
I just want you. I just want you. The words I never said but wanted to. I'm losing you. I'm losing you. Oh, but these thoughts won't let you go. They keep running back to you. Whoa. Can't look the other way. I'm chasing starlight to find its died away. Breathe it in. It's just now. We're just falling, and we won't always free fall back to nothing. 'Cause I'm just starting to learn. I've always been chasing
reasons why I need to hold on to everything. I don't know what to say now. I need to hold on to. Take much more now. I can't hold on to everything. I don't know what to say now.
it to the color of the normal, and it will become colorful, like that. Basically, if we have normal, if you understand what normal is, like each vertex, it's actually a vector, the direction where the face of the model is looking to. So we have RGB channels turned into XYZ turned into RGB. So red becomes an X, green becomes an Y, and blue becomes Z. So you can see, like, if you can draw like those axes, you can see why the colors are so made this way. And last thing, last magic I can show you, if I modify the position of a vertex by some random value, random algorithm, it can be like distorted in real time. So this small animation is done purely on the GPU side. So only thing which is CPU is doing here is getting the value of the time currently, which passed from the beginning of application run, passing to GPU, and all the transformations done by GPU. Just a small example of how GPU works. Another, maybe a little bit more complicated example, I will show you faster. Like that. The whole 3D scene is rendered purely by GPU code. So again, the only thing which is CPU calculating is the time value, how many seconds like passed from the beginning. And this is actually done by ray tracing, and this ball in the middle, it has real-time reflections from the outside environment. So some very complicated stuff can be done with GPU. GPU can also be used for just pure mathematics calculation. Due to its nature, GPU have only floating point data types for mathematical calculations. There are no integers on GPU, not like on CPU, which is mostly made for integer value types. And the main difference also, the GPU from CPU, is that GPU processor has no jumps. For example, if in the code I will write some if statement, something, it will be executed anyway, if I write it false. So if you have like some conditional statement in the shader code, both parts will be executed and one part will be ignored if you don't need it. This makes writing GPU code a little bit tricky, but it allows GPUs to execute code in massive parallel. Like GPUs can have hundreds of cores or thousands of cores, not like CPUs, maybe 8 cores. So this is like a small introduction about what is GPU. I will stop that so it don't eat my processor. So after the small introduction, I will probably skip this slide. I will start from the why I'm starting to talk to you about this. The thing is that recently, past couple of years, the vendors, the producers of mobile devices, they started to claim that mobile GPUs are not now so powerful that they can produce the level of graphics which are the same as for gaming consoles. And I started to examine the question, is it true or not? There are a lot of discussions on the internet, whether they're lying or it's just marketing or is it true? And there are no like real good analysis for that. I haven't found at least. So I did analysis by myself. So let's start. The values which are used by vendors of producers of mobile phones, they use spec parameters. Flops are the amount of floating point operations which can be made by GPU processor during 1 second of time. So gigaflops are the billions of those operations. And so from this table you can see that basically the vendors are right. So you can see that current modern mobile phones like Samsung Galaxy S8, which is a modern Android device, and iPhone 10, they already faster than previous generation of gaming consoles, and they're getting quite near the current generation. And if we extrapolate and consider the speed of growth of the mobile hardware and gaming console hardware, mobile phones will overcome the speed of gaming consoles quite quickly, from the first glance at least. So why do we don't see any example of good mobile games with good graphics? These are just two games I have played recently. On the left is a game with the picture produced by modern GPU for PC, and on the right is a game rendered by mobile GPU. So they still look different. Let's start from this picture. When I say GPU, usually guys, especially who are hardcore gamers, they know that GPU is a big piece of hardware which is stuck inside your computer, and it produces a lot of noise and gets hot quite often. Are there any gamers in the room who play games? Some, but not a lot. Okay. Who have GTX 1080 at home? No one. Okay. In reality, mobile devices, the GPU is a small part of the chipset, which usually contains both CPU and GPU on one chip. And this is, I think this is from iPhone device, and I think this is chipset A7, if I'm not mistaken. But it doesn't matter. The thing is that they have CPU, GPU, and here on the bottom is an output to memory, and both processor have used the same output and input to the memory chip. So, horror number one: why we cannot use the features which GPUs provide to us, made by hardware vendors. So horror number one is the API, graphics API. Historically, we are using APIs which were developed somewhere in the 90s. It is OpenGL, yes, and DirectX. And the API was never designed to meet the hardware features of modern GPUs. For example, the multi-threading is not possible. In the 90s, multi-core CPUs were not popular and were like basically not in like home PCs somewhere. So APIs were designed to have a global state, so you cannot send execution tasks from CPU to GPU in from multiply cores, from multiply threads. This produces quite a big problem. For example, if you have ever played a game on your PC and you switch to see what is like task manager is doing, you could see that only one CPU core is loaded to 100% and all other cores are just resting. Probably you see this problem, and this is actually the reason. The pure API is the reason. I will actually show you how it works. I will start a demo right away just to show you examples in real time. So I have iPhone iPhone 6s, and I'm running the same demo I just showed you on my laptop. So it's the same fractal demo with like a lot of GPU load on this for the rendering. And from the profiler, we could see that GPU is loaded. All renders are utilized almost to 100%. GPU is loaded for like 33 milliseconds per frame. This is like full load. Don't look at this thing right now. This is lying. It's just a bug of the profiler. But I will show what this GPU is doing. You can see that we have basically one core which is loaded for rendering, on all others are like doing nothing. This one occasionally doing something. Like basically only one core is loaded. So second problem with API is that all shader code, the shader which I just show you like this is a shader. all shader code shipped in your application as pure source. It is not compiled in the compilation time of your program. So all shader code is compiled in runtime when you run the program, basically on the device. And the compiler for the shader is a part of the GPU driver. So the problem is there are probably millions of different compilers, and not all of them are good quality. There are a lot of compilers who have some bugs, especially some syntax bugs. So you put some space between semicolon and like some compilers already failing. This is a huge problem. Basically, you cannot write single shader program, which is a little bit more complicated than simple, and be sure that it will be compiled by all devices the same way. API have poor memory management. When I showed you this picture, I told you that we have only one input-output to the memory for the CPU and GPU. Historically, all GPUs had a separate memory from your normal RAM, which is used by CPU. This is a good thing for GPU because it usually requires much faster memory. But in the mobile devices, probably there are not enough space for two memory chips, so usually those use the same one. Why we could use one chip in some better way than two chips? When a CPU makes, it's called a draw call to GPU, like it sends a task for execution, for rendering on the screen. It prepares a lot of information. For example, all the models which should be rendered, all the textures that should be rendered should be copied from the CPU memory to the GPU. And this is actually not required when you have the same memory. You could only send pointers to, okay, there I have texture, there I have model, but all the API actually doesn't allow it. We have the same memory chip, but we still must copy all the data from one part of the same memory to another just to make a render call, which is totally stupid. APIs don't have programmable blending. I will explain you what blending is. For example, in this example which we had with our sphere, oops, shader is not compiled. I think I have, yeah, I don't need this one. Never mind. Okay, I don't want to search for it right now for the bug. Okay, the blending is just how the pixels are rendered on the screen. If we have a sphere, currently all the pixels of the sphere, they replace the pixels which are rendered by the background shader. But if we could make blending more different, we could take a value of the pixel on which is currently in the frame buffer and add it to the pixels which are rendered by the sphere shader, or multiply, or any kind of other operation. The problem is that historically all blending was done using hardware. So all blending modes were limited by a set of limited fixed functions because they were already pre-implemented on the hardware side. Maybe not all, but most of the modern GPUs, they implement blending on the program side. So basically you could write this as a formula, how to combine two colors of pixels, background and foreground together. But API doesn't allow it again. So this could be used for optimization of rendering. And we have no performance guarantees in the API. For example, if you execute a program, GPU driver could start doing something at very inappropriate moment. For example, new texture arrives in the memory with new formats, and driver decides to recompile all the shaders it has in memory, and the whole application just hangs for 1 second, and then you receive those lags, visual lags in rendering. Ideally, it could be that the program could say to the driver, now I have a loading screen in front of my user, do all the necessary computations right now, but not later. It is not possible currently. That's why all the games and all the graphics are laggy, and graphics programmers cannot do anything about this. So, how can we fix those problems with APIs? Recently, basically, it was 2016, maybe you heard about it, the new generation of graphics API was announced. Vulkan have to replace the OpenGL, but we still have the war of the standards, and Microsoft and Apple, they released their own standards, and Metal was released by Apple as a replacement of OpenGL, and DirectX 12 we didn't change the name, but basically it's totally new API, not backward compatible. So yeah, before we had 2 standards, now we have 3. So that things are not moving good direction in this sense. But new APIs, they have no global state, so rendering is possible from multiply threads using multiply cores of the CPU. It is possible to manage your memory, so it is possible to ask from the GPU driver whether we have a single memory chip or 2 memory chips, and then you use this the way you want to optimize your code. The good thing is that there are no differences now between mobile API and PC, for example. Before we had OpenGL and OpenGL ES for mobile phones, like a subset of functionality of OpenGL. And yeah, standard war continues, as I said. Some people say that new APIs are overcomplicated. It is much harder to write a program using new API. But this is it's actually not so true. That when you have a team of programmers who work on some graphically intensive application, you only have a small part of the team which is working directly with graphics API, and all others are using some wrappers like written above it. So it's not a big problem. You have more problems only for a small part of the team. And most of the developers, they all already use some open source wrappers or some engines like Unity, for example, who already make the implementations for you. The bad news is that WebGL, they stated that they are not going to use new standards. They're not going to move to Vulkan API exactly because of this problem. They said it's too complicated. They said that performance is not so critical for web applications, though there are some games written on WebGL working in browsers. So they are not aiming for high-end performance. They just need things to work. So WebGL will not move to Vulkan. And the main question is, this is horror, this is fixed for the horror, when we will get it? My estimation is that maybe in 10 years, graphics programmers could rely purely on new generation APIs. So there will be a lot of devices left for old APIs for many years to come, I think. So maybe in 10 years we will have a fix.
But 10 years ago, OpenGL was, DirectX was a thing too, you know.
Well, actually, DirectX is still a thing. For example, there are still most of the games, at least PC games, they are released only for Windows platform exclusive. They all use DirectX. For mobile devices, for sure, DirectX is not a thing anymore because no one have Windows phones. Who have Windows phone? No one. That's what I thought. Or maybe there is one person who was just too shy to raise a hand. So yeah, Windows Phone is dead. No one cares about it. So Metal and Vulkan mostly. Horror number 2, heat. The problem is, again, I will come back to this slide. Devices which you have inside your PCs and consoles are really big pieces of hardware with effective ventilation and cooling. This thing doesn't have anything like this. All pieces are packed very tightly, and it relies, if it gets overheated, it relies on natural cooling of the phone, which is very poor actually. And every phone has a special mechanism to prevent burning. So if the phone would overheat without any limitation, it will start to burn in your pocket or in your hand eventually. So every phone has a mechanism called throttling, which lowers the frequency of the GPU GPU and CPU to produce less heat and make a device cool. This is very good thing for the device, that it will not blow up or start burning literally, but it's very bad for the user. So the user has user experience gets much worse when throttling turns on. Everything starts to lag, FPS falls, and probably I can show you the throttling mechanism in work, maybe not yet. So I started our application maybe some minutes ago, but it still has 30 frames per second, so throttling not yet turned on. We will see maybe in the end of my presentation, we will see the example of throttling. So this problem makes device resources unreachable. Basically, as a graphics programmer, I cannot use 100% of resources which the vendors of GPU give me. And actually, GPU vendors, the producers of GPU are aware of that, and phone producers also. For example, I think I can already switch to the next slide. This one, I made a small test. Oh, sorry about Russian. Forgot to translate it. I made a small test with Galaxy S devices. I had 4 Galaxy S devices by Samsung, and I made a small test for it. I wanted to see how many vertices and how many pixels device is able to render in 20 milliseconds, for example. And I made a measure only after the device was working full power, fully loaded, CPU and GPU after 10 minutes. So Galaxy S4 had 500,000 vertices rendered in 20 milliseconds, very good. Galaxy S5 rendered almost 1 million of vertices. And both phones didn't overheat. So after 10 and even after 20 minutes, I checked, throttling did not switch on. And Galaxy S6 had only about 250,000 vertices rendered, because after 10 minutes it started to throttle, and the same for Galaxy S7. So basically, the last phone which was balanced natural heating and the power of the processor is Galaxy S5. Everything which comes after Galaxy S5 is actually bad. Don't buy those phones. Because I don't know how it happens inside Samsung. I could imagine that there is a team of engineers which come to their marketers and business guys and say, hey guys, we cannot do this phone, this powerful, it will overheat. And they say do we have something written about overheating in the phone specs, official phone specs? No. Put the most powerful GPU as you can inside. No one cares that it wouldn't actually work. So the problem is marketing, because those companies are selling phones and users, the consumers, they choose phones by the specs. So for sure you will choose to buy a phone which costs the same, but has a faster GPU or more memory and faster CPU. You will buy this phone, but now no one actually tells you that no application could use this kind of power which is put inside your phone because of overheating, for example. So, how to fix that? Well, the first idea, vendors should end the spec wars. So they must be honest with their consumers. They should say like, wait guys, we cannot make our next phone 2 times faster as we did last year because we have this problem. And now you just buy a new phone which is same as last one but a little bit more expensive. Maybe it won't work. I don't know how it will work. So this problem should be actually solved by marketers, not engineers. The reality is that if vendors will put lower end chipsets inside their phones, graphic programmers like me could use it to make better level graphics than the current phones. And this trend actually is already seen in Apple. For example, last 3 phones, iPhone 7, 8 and X, didn't actually increase the speed of a processor. So the very first slide which I showed you, that's Galaxy S8 and iPhone are reaching the current generation of gaming consoles. iPhone X and 8 and 7, they all have about 350 gigaflops of speed. And they actually never advertise this. If you saw the last presentation from Apple, where they announced the iPhone X, iPhone 10, as always, they said, this is the best and the fastest phone we ever produced. They didn't say that actually GPU is the same. But they probably already heard iPhone 10 is the first phone which has GPU made by Apple customly. Before that, they always used GPUs designed by Imagination Technologies of Power VR series, so not their own. So iPhone 10 is the first one to use their own GPU, and there is a point why they did that. They wanted to consume less power. So basically the phone is, the GPU speed is the same, but it consumes less power. And this was advertised for consumers as a way to reduce the battery consumption. But in reality, I think they are aiming to get rid of overheating without adding some additional coolers to the device to still make the device smaller. So this was the point. But no one actually talks about it for some reason. And in the future, this problem probably will be solved. So other companies will also look at Apple, and this problem will probably be solved by making GPUs and processors consuming less power, so they will overheat much slower. And probably some cooling methods will be invented. I don't know, some new phone cases which radiate more heat, so it will cool faster. I don't know. Basically, right now we are near the singularity at this point. No one can predict what will be next year in this domain. So how do we avoid overheating? For example, in our project, we calculated that average playtime, average play session for our game is about 15 minutes, so on mobile phone. So we decided that we should guarantee that even on the toppest devices, which has unbalanced processors, we will guarantee to the consumer that we will have 30 frames per second for 15 minutes at least without overheating. So this way we will satisfy most of the customers, most of the players. And by making some experimentation, we ended up by using only about 60% of the device resources. So all those gigaflops, which are like advertised by marketers, producers of the phones cannot be used by us, only for 60%. And if you have an application who must have a play session with very intensive graphics rendering, more than 15 minutes, you will have to reduce the utilization of the processor even more and make basically your game or application look like, I don't know, outdated. So horror number 3 are tools. Unfortunately, there are too many vendors who make GPUs for mobile devices on the market right now. And there are no standard way to connect, for example, profiler or some analytical tools to the GPU so to get some information. So every vendor creates its own tools. So we have different tools for Adreno Snapdragon, for ARM, for PowerVR, and so on. And hardware vendors are known to be the worst software developers. So all those software pieces which must be used by developers are absolutely awful. They crash, they don't connect to the phones, they don't give enough information. For example, Apple is considered to be one of the best vendors who make good tools for the profiling of GPUs and CPUs. Until now, we can see that integrated profiler in Xcode, it gives us the CPU consumption 0 milliseconds, which is, I know that it's not true, because when I go switch to CPU tab, it is fully loaded. At least one core is fully loaded. So this is it's lying. It's a bug of the profiler. And even this profiler has bugs. Like all of them have even worse bugs. Especially it's true when producers of mobile phones, they buy the design of the GPUs, for example, from third-party vendors, and they close all the holes which are used by the profilers. So there are some devices who cannot be profiled at all, especially some no-name Chinese devices. There are all ways to connect to the GPU are closed by the producer of the phone, of the device. And Apple actually is doing this. For example, Apple, as I already said, is using PowerVR in most of the phones except iPhone X, the first one without PowerVR. And all PowerVR tools are blocked by Apple. So you cannot use PowerVR official tools to profile GPUs on iPhones. Well, at least Apple makes its own tools for that. And there are more vendors like that. So will there be better tools in the future? Probably not. Probably there will be even more vendors for GPUs to make, because like Apple is already becoming a vendor for mobile GPUs, and it's like there are more and more coming to the market. So how to solve this problem? Probably one solution is to make your own tools. For example, big companies who like make big budgets video games, they all make their own tools for profiling and so on. They directly communicate with vendors to make their own ways to communicate with hardware and so on. But if you're a small company who doesn't have resources for that, there are still some ways to optimize your work. For example, not so many people know that Google Chrome has a GPU profiler built in. So if you go, I will launch the Google Chrome. So if you go to Chrome tracing, it's a GPU profiler basically. Probably I can even show how it's working. Stop. Yep. So it splits out some information about GPU, which was consumed right now. Let it be consumed right now by Chrome. But the good thing about it, it has a function to load data and to save data. So, and the format of the data is very nicely documented. So if you're making your own application and you want something which will look like a GPU profiler to study the data, you can basically write a small script to spit out the information you need from your application to JSON file in the correct format, and then study the data using Chrome tracing. So this is one of the ways to optimize your work. So you don't have to create your own IDE for the profiler. And I think last version of Unity can do the same, but in different format. And the last horror number 4, is diversity. Probably not only unique for mobile phones, but still there are a lot of different devices on the market, hundreds of different chipsets, probably thousands or maybe even millions of different combinations of different CPU, GPU, and memory. And some configurations are inadequate. For example, some phone producer installs a very powerful GPU in the phone, but CPU is not powerful enough to serve this GPU. Or GPU and CPU are both powerful, but not enough memory to use all the resources, and these kind of problems. This is especially true for no-name Chinese devices, and usually Android operating system. And to fight that, usually when graphics programmers which make games for PC, they allow gamer to choose manually the configuration of the graphics. But it doesn't work for mobile devices. So mobile gamers, they don't know anything about those algorithms, and they cannot choose them or settings, those like very advanced hardware, advanced graphic settings. They cannot choose it. So they have to be chosen automatically. We use the model of the device itself for iOS operating system, because there are not a lot of them, to make the graphic settings like choose automatically which post effects we're using or which like loading level we're using. And we use the model of the GPU chipset itself for iPhones. But you should remember, you can never satisfy everyone. There will always be some device your graphical application will like give inadequate settings, and it will be not good speed of rendering. And in conclusion, I might say that mobile devices did not reach the level of gaming consoles. So this was the question in the beginning. No, it is not possible to make games or graphic application with the same graphic quality as gaming consoles, and it wouldn't be in the nearest future, I think. So those marketers of mobile companies can, I don't know, shut up, something like that. The thing is that mobile devices will never be made for graphics. Mostly mobile devices are made for simple tasks like reading emails or browsing your Facebook, which doesn't require a lot of performance from the hardware side, from the graphics hardware side. And gaming will always be a bonus. And if you want to play games with good graphics, better buy yourself a gaming console or play on PC. Don't play on mobile phones. So, thanks. That's all.
Now we have a bit of time for questions, exactly 3 questions. I think we can fit in before we have a break and then proceed to the last talk. So first quick question by Dmitry.
Regarding this memory management, I remember from like beginning of 2000 something or 90s, there was a thing called direct memory access for graphic cards, and graphic cards could read from memory.
From a CPU memory, I mean.
From main memory. They usually, I think, copied that part of memory to their own video memory before processing, but it was possible back then. And it's like 17 years passed and mobiles could not get this working.
Maybe what the thing
Why?
maybe the thing you're talking about is was some kind of hack because it never been a part of official graphics API. So like to read directly the CPU memory, and even that's the reason of the problem. That's even if you have the same memory for both devices, there is still no way to say to GPU, please take your data from this part of memory just because of API. Maybe you mean some hack which was developed by some smart guys in the 90s.
Don't remember.
But yeah, it's not really possible right now. I think it should be possible using Vulkan API, and only on device which have like combined memory. But I haven't tried it yet.
Okay, any more questions?
I can always ask questions.
Sure, go for it.
So Firefox is going to launch.
We want it?
No, I'm fine.
But here we get it.
So there were 2 days ago, I received a tweet, or there was a tweet in my feed that said that Firefox is going to launch some kind of a new web render, which is an engine that's using GPU a lot in a very nice way. It makes some of the rendering things very fast. And so when I read this article, they mentioned that they're pushing towards being able to render 4K images and displays and videos and all that stuff in a very fast way. So that's the direction that they're going to. So first question would be, have you done some work on being able to do these kind of graphics modeling games on browsers? Are you going to? And how do you see that kind of industry going? How far is that I'm going to play a very, very good 4K video game in my browser?
Okay, you are actually asking about two completely different things. One thing is that browser is using GPU to render HTML and CSS. This is one thing, and the browser can use GPU on very low level to do this. I think Chrome is already doing this long time ago, and I think Firefox too. I don't know what kind of news. Maybe they will continue to make it expand the use of GPU or something like this. But they already do it. And the second thing you're asking, whether I can make a web page with JavaScript to utilize GPU to render stuff directly in the browser window. These are actually totally different domains. One is like HTML, normal HTML rendering, and the second thing is like this HTML canvas using GPU. And as I said, it is already possible to make nice graphical applications using WebGL, which is JavaScript API for OpenGL, yes. But guys from who make this WebGL standard, they said that the performance is not their main goal, so they are not switching to Vulkan as all other devices slowly. WebGL, like GPU graphics on the inside browser, will always stay some kind of like toy, like a bonus feature which is rarely used, I think.
Maybe after some years.
Maybe after some, do you think maybe they will switch to Vulkan when it will prove that it's like makes sense to use it? I don't know. But I think all browser applications will always be behind for rendering algorithms and so on after the standalone applications. That's for sure.
Okay, cool. Thank you. And last question, maybe? Anyone? All right. Yeah.
What are the challenges in bringing discontinuous rendering methods?
Can you take it as cube? Nice blue one.
Yeah. So what are the challenges in bringing the discontinuous gathering methods to GPU?
What are the challenges of bringing what?
Okay, I'll get back to you later.
Okay, I just didn't get it.
Speaking to the queue. Okay. Discontinuous gathering methods.
Scattering. Sorry, I didn't get.
Continuous gathering methods.
Scattering.
Gathering. Aggregating.
Aggregating methods.
Yeah.
I didn't get it. Sorry.
Gathering method. Mathematician.
What kind of gathering?
Gathering methods.
Algorithm.
Algorithm methods.
Algorithm.
Gathering was a mathematician.
Sorry, let's talk about it on when it will be break.
You guys can have a chat during the break time. So thank you, Filipp. Thank you, guys. Let's have 5-minute break, or maybe 7-minute break max, and get back together for the last one. Thank you.
Direct memory.
In the spirit of things, we lose our sight when we put our trust in things of this material world. The things that fade away, yet we keep coming back, 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 keep coming back. Of things we know, Give me reasons to doubt, try to keep me down, but I'll put the flame out. You can't get to me. Throw your sticks and your stones, go break all of my bones. You won't ache my soul. You can't get to me. And there is no barricade that I can tear away. Shoot me down, go fire away, away. But I'm a heavyweight. I'm a heavyweight. I'm a heavyweight. I'm a But I'm a heavyweight. I'm a heavyweight. I'm a heavyweight. Push me down to the ground. What goes around comes around. You won't put the flame out. You can't get to me. Say what you wanna say. Go take it all away. But I'm here to stay. No, you can't get to me. And there is no barricade that I can tear away. Shoot me down, go fire away, away. But I'm a heavyweight. I'm a heavyweight. I'm a heavyweight. I'm a heavyweight. But I'm a heavyweight. I'm a heavyweight. I'm a
Okay, please welcome Erkki Alamäe from Nortal to stage, and let's greet him with a warm applause.
Good evening, everybody Can you hear me in the back rows? Just making sure.
Somebody said no, actually.
Okay, well, I'll try to speak up a bit then.
You want to put headset on?
Uh-huh.
Just plug it in. This way around, I think. Yeah.
Okay. Can you hear me in the back rows now? All right. My name is Erkki Alamäe, and I'm a data scientist at Nortal. And I will talk to you today about what you can do with your data. So first, some introductory words, then a bit about the groundwork of data science, which is cleaning data. Then most of this presentation will be what next, what to do with the clean data, and then finally some tips and tricks about data volume and computing power. So a few words about me. As data scientists tend to come from different backgrounds, here's mine. I was a system analyst actually for 7 years. And then about 2 years ago, I discovered the diverse and interesting world of machine learning and data science for myself. So since then, I have been learning and practicing it, basically. I made some assumptions about you as the audience to put together the slide set. I assumed that probably you have run SQL queries, NoSQL queries, that you have done data cleaning either manually or using scripting, that you have used spreadsheets, formulas, graphs, but this is where my baseline is, basically. So everything that I think is above that level, I will talk about. Not to bash Excel in any way, because there are also many methods presented here that you can also do with Excel, but that's not the point of this presentation. I will be talking about the methods themselves. Not to bring any fear into this, just to maybe take off some of the pressure. Here is a quote by author of a book I read recently, and he basically said that at its core, data science is about spotting patterns in data and seeing how one variable affects another. So in no way is it rocket science. The data science process on paper looks like this. You formulate a hypothesis or ask a question. You then acquire data to validate it. You then clean and analyze the data and end up with a result. Well, at least this is how we would like it to be, or how I would also like it to be. But in reality, it's not like this. It's not straightforward, and there is a lot of back and forth between the stages. Another way to visualize it would be to draw a graph where on the one axis you have time, and the other axis you have the number of questions and answers that you have asked and that you have answers for. So based on my experience, the number of answers throughout this project rises. It's not necessarily a linear curve, but it goes up. And the number of questions, when we start, we would like to think that it's a constant, that it doesn't change. But what I have seen is that it rises, and often it rises exponentially. So you usually end up with more questions that you have answers for. And this is the uncertainty. you basically never know what you're going to get when you start out. But it doesn't mean that you won't get anything. And I'm not going to talk about this process at length. This talk is not about that, but when you use the tools that are there, you need to keep in mind that there are sets of assumptions that need to be filled in order to use those tools. And if you make wrong assumptions, then down the line you will make mistakes and you will be using the wrong tools, which will give you the wrong results. Another way to look at the data science process from a helicopter view is that data science is not a Kaggle competition where you have a data set, you do some voodoo magic, and you get a nice predictive model. It is part of data science, true, but everything preceding that, all the work put in before the data set was published on Kaggle is a lot of work, and some people estimate it to be between 60 and 85% of all the work put in. And already during that stage, a lot of decisions get made. What features do I select? What features mean what? And so on. There is a process that is followed. Granted, it's not deterministic. And there is a toolbox or a set of tools that are used. And just to reiterate, that is not the sexy part of data science, but this is the part that we usually end up spending the most time in. A few more introductory words before we get started. There is no silver bullet. I heard this also mentioned in 2 talks before me, but the good news is that probably each of you have access to some data sets that are not public, that maybe are proprietary to your company, to your wherever you work or who you work for, and that's already a great start. Cleaning data. Cleaning data is required when we have data that has a low signal-to-noise ratio, where it is hard to extract meaning out of it, just without it being processed first. So what is then done is often called by different names. Some names for it are cleaning, pre-processing, data munging, data wrangling. They essentially mean the same thing. So this data, it can be audio, images, log files, databases, scraped websites, you name it. In this form, we cannot use the data directly, but what we do then is called feature engineering or feature extraction, where we, for example, in the case of a log file, we take each row as a row in a table and then start adding columns to it. We extract the features one by one. For text formats, there are many tools to do it. There are specialized libraries for JSON, XML, HTML. For nice log files, you would usually use regular expressions, lots of them possibly. And for ugly file formats, or some, I don't know, custom formats that no one else uses, well, this is when your scripting skills come in. During data cleaning, it is very important to spend as much time as possible cleaning the data and visualizing it at the same time. Getting the distributions, getting to know, getting a gut feeling about the data. For example, finding the average. If we plot a feature on a histogram, we might be tempted to immediately say that, well, let's find the average, which we just calculated mathematically, and it's this arrow in the middle, that's the average. Whereas if we take an additional feature, use it to highlight the individual distributions within this larger distribution, we now see that we have 3 different normal distributions, and finding averages for these is actually a lot more meaningful than finding the global average, because the global average might not give us anything to work with, or might lead us to down paths that lead nowhere eventually. There are 2 formats used which are kind of equivalent. There is the long format and there is the long format, long and wide, sorry. And they are semantically equivalent, and you should have no fear about moving between those formats when one step requires it or the other. Usually moving between them is just one single line of code in your data processing pipeline, in your language of choice. This is transformation is called also with different names. It's cast, melt, spread, gather, unfold, fold, depending on the context. Some people just use different names. One thing you will quite often encounter are missing values in data. And here I have just given an example that one option would be to replace it with a median value, where you would just fill in the values based on medians. But this is something where you already need to be very conscious about the decisions that you make, because if you start filling in values, you need to be aware that in the end it might skew your results quite badly. And you might need to come back to this stage actually and choose a different strategy. For example, if the results don't make sense, then you come back to this stage and you choose a different strategy. One method I use quite often is called LOCF, or last observation carried forward, which is used when you have a time series which has sparse values. You might have a value for one date, then 3 days when you have no values, and then again a day where you have a value. If you have reasonable expectation that the value in the middle did not change, you can again use a one-liner to fill in the missing days. Again, this is an assumption that you make that you might need to come back to. And in the more complex cases, the data set might actually require you to fill in values that are not actually there in the data set. Here, for example, we can see that we have joined 2 data sets, one that has a date and one that has a time and value, but none of them are complete. So to make them complete, we have to use custom logic. This is something we again need to have an excuse for, so to say. So in the date column, we have decided that going forward, we will use the date that is given, and going backward, we will look at the time value. If it has changed from 00 to 23, we will assume that it's the previous date. And for the value column, we have done also backwards propagation, not forwards. But this again is an assumption. It might have been done the other way. You will encounter outliers. And again, you need to decide what to do with them. You might have to fix data manually. You might have to go to the data sources to fix it, but usually it's quicker just to do it than during your analysis. But that's not sustainable. So you have to pick a path between those two. In summary, data cleaning is estimated to take up a lot of time of the data science process. can include fixing data manually. It can actually get long and complicated. And you might need to come back to the decisions that you made. So now, assuming that we have clean data, we are ready to start creating models and to analyze it, not to visualize it anymore. So the tools that can be used. When you don't know a lot about your data, then one method that is used is clustering, where you take data and apply certain algorithms to it that will make subgroups in this data. Clustering helps you understand data and helps you form assumptions. Actually, visually identifying those patterns in 1D, 2D, and 3D is quite easy. Well, you just look and you maybe apply some colors, and already you see groups emerge from the data. But what do you do when you have more than 3 dimensions? Is there a way to compress this 4-dimensional space into something that we can visualize and then find patterns out of it? Well, it turns we can, and let's use an example. This is a classical one. It's a data set of flowers published in the 1930s by a biologist, and it has 4-dimensional data about a species of flowers called iris. The data that is there in the data set is the length and width of the parts of the flowers called sepals and petals. And we will, to demonstrate clustering on this dataset, we will use something called PCA, or Principal Component Analysis. Again, by analogy, Principal Component Analysis works like lossy compression. Say you have a bitmap image and you need to do something with it. Well, first off, if this bitmap image is so large that it won't even fit on your hard drive, then you can't do anything with it, basically. You're stuck there. But you might apply lossy compression, for example, to get a JPEG, and then already you get something that you can work with. Similarly, Principal Component Analysis compresses high-dimensional data into lower-dimensional data, or at least it gives you the prerequisite data to do it yourself. By example, this is a data set, 2-dimensional one, that we will apply Principal Component Analysis to. What Principal Component Analysis does, it finds vectors in the data that describe the data best and orders those vectors. So it kind of reorients the axis in the order that allows you to describe the data best. For example, in this case, we got that Principal Component 1, or PC1, accounts for 99% of the variance. We can see that the dataset has a lot of variability in the diagonal direction, where PC1 is oriented, and PC2 is only 1% of the variance. So based on this, we might decide that, well, hey, let's drop PC2. We don't need it. At least for clustering, we can just drop it and then move on just to PC1. And then we have a 1-dimensional data set. If it were a higher dimensional data set that we got down to 3 dimensions or 2 dimensions, that would already be useful. But this is just to give an example. So applying this Principal Component Analysis on the iris dataset gives us that the number of dimensions, as it lessens, this is a graph that shows that how much information do we still get to keep. And we find that if we keep the number of dimensions at 2, then we still keep 95% of the variance of the original data set. When we apply this lossy compression and then decompress back into 4 dimensions, then this is what it would look like visually. So here is the uncompressed data set. Here we have dropped down to 3 dimensions, 2 dimensions, and 1 dimension. Again, 4, 3, 2, 1. So what does this data set look like in 2-dimensional space? It looks like this. And if we draw the dimensions of the original data set in terms of the new PC1 and PC2, this is what we get. We have a feature sepal width, which is quite an important distinguishing feature, and then are all the rest, all the other 3 components, which are kind of similar to each other. Now, having compressed this data 4-dimensional data into 2D, we can start finding clusters. And for example, if we decide that we want to have 2 clusters, this is what it might look like. Or 3 clusters is what it would look like in the middle. And for reference, the original data set, which also had, in addition, the actual species that the flowers were, looks kind of similar. You can see that we have lost a bit of information, and also the choice of clustering algorithm makes a difference. But in essence, this is how we found patterns in 4-dimensional data. And visually, we went from this, where we didn't know how those 3 species are related, to this. So this is 1 species, and these are 2 other species which are kind of similar to each other. Here we showed the example of 4 dimensions, but you can also go higher. For example, this is the so-called MNIST dataset consisting of handwritten digits, where each digit is 28 pixel by 28 pixel array, and each value is a grayscale value of that pixel. So in total, each image is 784 values of grayscale. And I didn't do this visualization myself, but actually a machine learning researcher named Christopher Olach did it. And here you can see the unclustered data set, which is, well, all the numbers are clobbered together. But now if we apply this iterative clustering algorithm, you can see in real time actually how it starts to cluster the numbers. So here, for example, we have the number 1s, here we have the 6s, here we have the 0s, and so on. But it's not pure. There are some which are in the middle of other digits and so on. For example, here we have a 7, which is somehow grouped together with 2s. And this also shows you one method how to find outliers in your data. This takes quite a lot of time, so the author has also shown an image that he obtained by quite a lot of parameter tuning. Well, this is the final result, so to say. And you can see, for example, here a number 5, which is grouped together with the 0s, or a number 3, which is put together with the 6s. And you also kind of get a gut feeling about why, or what makes it look so similar than the others in this group. So this was clustering. You can also do clustering on non-numeric data. For example, shopping basket contents. You find the graph which says that which items are bought frequently together. It's also a clustering problem. It's just that it doesn't involve higher dimensional spaces. Now a few words about anomaly detection. For numeric data, you might come up, for example, with an automatic rule to say that I assume that this distribution is normal, and I will automatically label everything that is, for example, 2 standard deviations more or less than the average as outliers. So here we have done exactly this. We have automatically, based on some assumptions, found some outliers. For time series, some specialized algorithms exist, and here is an example from Twitter's time series anomaly detection algorithm, where it is a multi-stage algorithm where you first find the seasonality of your data. By the way, it has to be seasonal. And then within those seasons, you start finding local anomalies and then global anomalies. For example, we might say that this is around Christmas. Maybe people tweet a lot during Christmas. Or maybe it's New Year's. I actually don't know. And then there's always visual anomaly detection. So you just, you as the researcher or analyst, however you like to call yourself, look at the data visually and try to find which of those values that you have in your dataset are anomalous. It is purely up to your choice, and you have to reason about the choices that you made. But you might, for example, decide that these are the outliers, because they are the farthest from the group center if you look at this dataset visually. Or in the right-hand side, you might consider that this blue flower that somehow ended up in the middle of the green labeled flowers is an anomaly. Maybe it was mislabeled when the data was input. Maybe it was not. Maybe it just was exceptional. In either way, this is something, again, that you might have to come back to later on to revise your assumptions and maybe choose a different strategy. Modeling. Now, this is now something that would be considered sexy, or the sexy part of data science. Modeling, or some call it classification, allows you to fill in the missing values based on previous data. For example, we might predict that the price of an apartment based on rooms and square meters based on previous data. The simplest way to do it is linear regression. You just draw a straight line using a linear algebra method, then pick a spot where you want to get a prediction, and then just pick the point on the line. But there are other techniques as well, and I also heard them mentioned during this first talk about Spark. One of them is decision trees or random forest, if you have many decision trees, where you tell the computer that, well, the solution to my problem should look like this. This is the model that I should have. It should be like a tree. It should involve decision points throughout this decision-making process. And I want you, the computer, to tell me what is the most optimal solution to my problem that would predict my Y column in the best way. And then you go through model training, and you get this trained model, which is the set of decisions or the set of parameters that decisions that you need to make in this decision tree. A neural net is similar to it, except that you tell the computer that, well, the solution to my problem should have this structure. It should look like a neural net where neurons communicate with each other. Again, you give it an input, an output, and going through training, you get the weights or the parameters of the model. But there needs to be some caution when applying those models. There is the real danger of overfitting, and the overfitting is demonstrated by this green line in the middle. When you train a model to be perfect, then there is the danger that it will start distorting reality. When you have an overfitting model used to influence real life events, for example, if a model would determine someone's salary based on something that they have done in the past, this might really start distorting real life. And in these cases, the best advice that I have read myself is that you should employ human judgment in the decision-making process. Feedback is important, and you need to actually re-evaluate the model periodically. Forecasting is a special case where you are not predicting not just one value, but you are actually predicting many days into the future. And this is useful for time series, again. And forecasting might give you this predicted line and some upper bound and some lower bound, for example. Another specialized kind of algorithm is called process mining, which can be applied to so-called event data, which in a minimum should consist of the process ID or the trace ID, a timestamp, and the step identifier. And if you have data that is formatted like this, you can actually use specialized algorithms to kind of let's say, reverse engineer the process model and start reasoning based on that. So by looking at the model is much more intuitive for a person than looking at the raw data. So that was modeling. Now something called optimization, which is a bit different from modeling because there are a few tricks that you can use with optimization. There is a special class of optimization problems called linear programming. And with linear programming, if the problem is well defined, then actually turns out that the solution to your problem is one of those corner points A, B, C, D, or E. And you actually can skip evaluating all this parameter space or solution space. But this is only if your problem is formulated in that way. There are also specialized optimization problems for different subdomains, like the vehicle routing problem, which you might define in other contexts as a machine learning problem, but there are specialized algorithms for it. Use them. And lastly, joining two data sets. Although it's not an algorithm at all, or a method that I could give a talk about, it's something that I have found useful personally. Just by linking two data sets, you create a lot of value. For example, you might decide if you have a set of location time series data about vehicles to link it with the locations of nearby, let's say, restaurants or gas stations or police stations, and start finding whether those routes and whether those points of interest have anything in common. A bit about advanced things. And these are things that you can do once you have a trained model. One example would be optical character recognition, where using the trained model, you can use the model to derive text from images. Using a special class of neural networks called autoencoders, you can actually do denoising. If you have the trained model and you give it a noisy image, then the model will take the noise away by using its internal compressed representation and then using that in your reverse. It's kind of doing lossy compression and then decompression, that the analogy that we used before. Here is an analogy or use of a trained machine learning model from the domain of raycasting. On the left-hand side, there is this halfway ray-traced image. And the researchers at the graphics card manufacturer NVIDIA found a way to teach the model how to predict what the next pixels would look like. And on the right, you can see the output of that algorithm. And using that trained model, they could speed up the ray tracing process by 4 times. Another thing that can be done is named entity recognition, where the model will tell you whether text contains references to living persons or places in real world. A quite cutting-edge example would be generative adversarial networks, or GANs, in other words. And these networks are kind of like making the computer play chess against itself. There are 2 players. One network tries to generate images and the other network tries to say whether those images are real or not. And you end up with these examples here. And these examples all have one thing in common, which is that none of these bedrooms exist. They have been generated by a computer model. Yes, they are based on real life images, but they don't exist in real life. Lastly, a few tips about data volume and computing power. Again, not to bash Excel in any way, but Excel has a hard limit of 1 million rows. On your laptop, you can do 100 million rows or more if you compress and pack data the right way. For example, the Java virtual machine has a 12x overhead for strings, for small strings. For large strings, the overhead is smaller. Once you have packed the data well, then the next option is that use more RAM. Just add more RAM sticks. And lastly, you can work on subsets of the data or samples, and you can parallelize, for example, using Hadoop. And a few words about computing power. When you have a problem to take that you do infrequently, then 0.01 second versus 1 second doesn't matter. It seems like an instant, but if you have 1 hour versus 100 hours, then already you start thinking how to make it quicker. Especially with large data sets, you need to discover what those dead ends are that lead nowhere and eliminate them as early as possible. And some tricks to do that would to look for optimized libraries. For example, libraries that are specialized for processing graphs. They even might be implemented on GPUs. Another option is using lower level languages. for example C, and then there is the possibility to use GPUs as well for computation. I personally have seen speed-ups in the order of 100,000, of which the first 10,000x was achieved just by going to a lower level language, and the last tenfold increase was going from CPU to GPU. Now, granted, it took me quite a while, because the lower you go, the more time it takes, because the lower level it is. But if you have a really large data set, then it might pay off. In the end, it's up to you to decide. And the most important thing is that you need to never lose your ability to iterate quickly as possible, because there will be dead ends. You will need to choose alternate hypotheses, move on with those, and so on. So in summary, we talked about cleaning data, what to do with the clean data, and a few tips about data volume and computing power. Thank you.
Okay, thank you so much, Erkki. We got a few more minutes for some questions to squeeze in. Anybody? Okay, Anton.
I wanted to ask, what is your typical task at work that where you apply all of this?
Every project is different. When I'm asked that how long would a project take, then off the bat I might say that it's 2 weeks. But what happens during those 2 weeks? Probably it's a lot of meetings. Probably it's a lot of getting data.
What do you do? Like, what is your job or assignment to use these things?
Bringing examples of cool results. Good questions.
Well, I can't speak about those, unfortunately, in too much detail.
Yeah, well,
every project is different. It really depends, but I can certainly say that this 60 to 85% rule of data cleaning is real. It does take a considerable amount of my time. Actually, just making visualizations and asking new questions based on answers that I got, asking for additional data from the client. If you're asking about what tools I use,
I'm asking actually an example of where do you apply all of this?
You mean like
What kind of
like maybe domain area?
Domain. I have analyzed industry data, for example, the factory machines, that the sensors that produce a lot of data, all kinds of sensors. Then I have analyzed location data from devices that move around, finding patterns in that. I have done process mining, where the objective is to find the path that takes the longest time, that's the critical path, and then the longer term goal would be to make that path shorter, but first you have to identify it. So those would be 3 examples.
Recently, I have noticed that in the news there are a lot of messages about some statistical studies are being rejected. For example, 10 years ago there was some psychology study with some 10,000 of people, and they decided that conclusions are this. But now, 10 years after, they take the same data, make data analysis again, and they cannot make the same conclusion. Do you think it could be that bad engineers who analyze the data are responsible, or the scientists who are more responsible for that?
Well, it could be solved if the code that was used to obtain the results was also published along with the research studies. So then it would be actually quite easily be repeated by other researchers. Whether somebody is doing it on purpose just to get published, or whether they made a mistake, is I think is anybody's guess, except for the people who did it.
For example, you're as an engineer, you're doing data cleaning, right? And for example, a client comes to you and say that, oh, please make data cleaning in this kind of particular way to make special results in the end. Do you agree?
Personally, I have not been put in that kind of situation before, but if I would be, then I guess I would say no.
Okay. One question from there. No, you.
So I have two questions. One is, do you often come across that more granular time-series data will give you better results? Or is it just the question you ask, or just the question you try to get answer for what matters actually? And the second question is about cleaning data. Can you give examples of universally bad collection of data? Meaning, one example, what I've come across is if you want to understand whether a person lives in an apartment or in a house and try to get this out from an address, it's quite difficult because people don't write their addresses in a very clean way. Is there other good examples of not depending on the country, that data is using that, and it takes a lot of time to work with this?
Okay. So the first question was about whether more granular data helps. Based on my experience, yes, it always does help. And I have seen cases where I have been handed a data set that has already been aggregated. They might think that there are a lot of useful things there. You have the average, you have the median, you have the minimum, the maximum. But it doesn't tell you anything about what happened in the middle in that time period. And that might be the thing you're actually looking for. So in that case, more granular data always helps. And if it's more granular than you need it to be, then you can always apply generalization on your own. The ground rule, I think, in big data is that don't delete it, don't aggregate it, just keep it. And then later apply a schema, analyze it however you might need to analyze it from whatever perspective. And then, like years later, you might decide to clean it, delete it, I mean. So that's my stance on granular data. So. And the second question was, could you maybe repeat it?
So I've come across that it's sometimes like addresses, home addresses are quite unstructured. So people use a house first, and then city, and so on, and some start with the city, and then go house, and so on. It's difficult to get out. Are there any other universally unclean data sets that you come across? Not depending on the country, or what can you say that this is going to take time if you see that this is in the data set, or you understand that, okay, probably you're going to have to work with that. And it's very complicated. Are there any good examples? If there are not,
I think addresses are a good example, but you already gave that one.
phone numbers.
Phone numbers, maybe not so much.
Some notes.
My team took part in a hackathon recently where we analyzed the public document registries, which are there publicly available for all, published by the Estonian municipalities. And well, although everything is there, it's actually everything is different. And if you want to kind of gather it all together and analyze it, then it actually takes a lot of time just to get the data. That's one example where you need to put in a lot of effort to actually get the data. There are no APIs to make your life easier. But I think I'm drawing a blank on the more examples.
Okay, the guy over there. The question is.
So, when we take genes of a person, we are able to derive their facial features by putting in more data. But the reverse is not possible. When we take the facial features of the person, we are unable to derive to the genes, to make a person. So, this particular problem, one of the leading biotechnology labs of Craig Venter is facing right now, and they have developed their own AI. Is it a standard problem that the things can be solved one side, taking this data set and getting another, but the same techniques cannot be used reversely?
So to sum up, genes can be derived from facial features and not vice versa.
The other way.
So the other way.
Take from a crime spot gene of a person, and you could send it to John Craig Venter's lab, and they could give you exact facial features of the person. But they can't do reverse. Like if you want those facial features and you want changes in your baby, for example, they can't design that.
So the question is how much of a pattern it is that the data can be only derived one way.
Yeah.
Okay.
I think it's kind of comes down to the domain, whether this mapping between the genes and the facial features is one-to-one. If there is like one facial feature that can come from many combinations of genes, then you can't decide predict which one of them it's going to be. That's just like the domain-specific part. But I think if we're talking generally, then you can go both ways. In the general case, I don't see any objection, because in the one case you would be predicting the genes based on the facial features, and the other case the other way around. It's just a matter of coding or classifying and saying what are the features that you need to predict based on what.
Sorry, Dmitry has something to add.
Yeah, if I may add, so it's always, if you look at the at information level, right? So from information theory level, there is information from one side and from another, and any process changes the entropy. And if entropy decreases with the process, you can't go back. It's just you've lost some data, and this is the nature of our just nature. Like hash algorithm, if you apply hashing function, you can't go back. As simple as this.
Well, you can look up the hash value from dictionary.
Maybe a better example is,
unless there are collisions.
Maybe it's easier to just say that the face is the comparison of the cheeks.
Is it an example?
Well, yes, if you have a linear regression model, then the mapping between the y and the x-axis is one-to-one. In that case, the model is, you could say it's purely mathematic, and there is a one-to-one mapping. But it's not always as simple as that. You don't have one feature predicting one another feature. There are quite a lot more.
Last question.
An easier question, I guess. What do you recommend, or what advice can you give to somebody that also wants to dive in all this data science field, I guess?
One book I really enjoyed reading myself was a book called The Data Science Handbook, where the book contains interviews by, I think it was 20 or 25 real-life data scientists. And it's not purely technical, and it's not purely, I don't know, social sciences, to use that term. But it gives you a really good gut feeling of where the field is and where to start, which directions you might want to go in. Because the field of data science is quite new, then there are not many established bachelor's programs or master's programs. And actually reading what the people have done is, I think, a really great way to get your feet on the ground. And from there on, I think you can already decide for yourself what specific tools you want to start learning first. So the Data Science Handbook, you can get it for free online.
Thank you so much, Erkki. Great talk. Thank you guys for joining us tonight. It was a great pleasure, and we are already planning something for you for November. Stay tuned. Check us out on the internet, Facebook primarily, and see you in a month or so. Thank you. Küsimused tulid ja siuke nagu elav vestlus tekkis, et väga nagu mõlemas selles.
Walking alone, the streets are empty. The only thing I can see is my own silhouette. I'm getting